Hi, this is ET370, and this is an example problem that I'd like to go over. It's a Zener diode, and the Zener diode is hooked up as a voltage regulator, okay? And I believe this is 10.25 on your homeworks, but let's go over the problem. So the problem basically asks is you have a Zener diode set up, and you have some load here, and that we want to maintain a constant voltage across this VL. In fact, we want to maintain a constant voltage of 5 volts. So you have a voltage source, you have a resistor, you have your currents defined I load, and then the I diode. And notice V diode and VL are the same, but just opposite sign by KVL. And what they're going to assume is this Zener diode is ideal, and they give you the fact that this VS could vary. So this could be anywhere between 8 to 12 volts, and that this current can be anywhere between 50 to 150 milliamps here. And what they want to know is what's the largest resistor here in this path such that VL remains constant at 5 volts, even with these two variations of the load current and the source. And then the next question asks, well, let's say you found what RS is. What is the max power dissipated in RS? And so that'll probably be when this is 12 volts, the max here, and this is 5. Okay, so that's pretty easy, but this one's the hardest to think about conceptually. Okay. So let's kind of break down, before we do any math, let's just think what's happening, right? Now, so this circuit is trying to behave like a voltage regulator, right? And we want to think that this voltage regulator is going to have the hardest time maintaining the constant voltage when more current is being pulled from this system right here. Okay, imagine this is like your wall, right? This is like 120 volts coming out of your wall. If you apply your toaster, your heater, your air conditioning, everything, you're pulling a lot of current, that voltage might droop a little bit, right? And so that 120 volts might droop. So the worst case scenario is actually when you're pulling more current. So that's going to be the 150 milliamps. The other thing you can think of is, well, what if your pump, remember the hydro analogy for voltage is pressure. What if this voltage pump back here is actually putting out the least amount of PSI? Well, if you're pulling more current, this thing wants to droop, right? And if you only have 8 volts or 8 PSI as opposed to 12, it's also going to have a hard time maintaining this voltage. So just from your physical intuition, you could reason that more IL is going to tend to droop this VL, and less VS over here is going to provide less robustness when VL tries to droop. Okay, so that means 8 volts and 150 milliamps are going to be kind of our worst case scenario going on here. Okay, all right, so we're going to save these two. These are your worst case parameters for when you're varying. All right, now what we can do is use our load line analysis. Okay, and what is the load line again? We're combining our Zener diode curve with our ET250 analysis, our Ohm's law and all that stuff, KVL. And what we want to do is we want to get an IDVD line, right? So that we can compare the two and find out what the operating point is. Okay, so let's go back to our little system here. I just basically redrew this, right? And so what's going on? I have nodal Ohm's law. Now be very careful. Look at this node voltage. I put a little ground here. The node voltage at this point is either VL or it's negative VD, okay, because of the way this is drawn here. Okay, so I can do an Ohm's law here. Current equals the node voltage Vs minus negative Vd over Rs, no problem. Or I is equal to Vs plus Vd over Rs, no problem there. KCL is going to say I plus ID equals IL, great, which means that ID is equal to minus IS plus IL. I'm just going to substitute this guy in, so ID equals minus Vs plus Vd over Rs plus IL, and I get this. Notice I pulled out the minus Vd over Rs over here, and the minus Vs over Rs, and put it over here, plus IL. And this is nice because this is y equals mx plus b form, right? You have the y, you have the x, which is Vd, you have a negative slope, and you have this y-intercept, and we can plot that on the Zener diode curve. And this is what's going to give us the load line analysis and the operating point. Okay, so imagine this is a negative slope line. So I rewrote the equation here, same thing. And here's the Zener diode curve in red, okay? So it's an ideal, so we'll assume no forward voltage is vertical. It goes horizontal, no current here, and then drops off vertically at negative 5 volts, okay? All right, I drew a bunch of example blue lines here. So these blue lines represent this blue line, or the ET250 analysis, the nodal Ohm's law of KCL, okay? Now let's look at what's going on. If I have an operating point that can exist on this vertical line, not here, what happens? Well, because KVL states that VL is negative VD and this line has negative 5 volts, well, VL is going to be positive 5 volts. Any operating point on this line is going to be nice because now we are matching, we're meeting our constraint that we have a constant 5 volts across that VL. This is good, right? This is bad. Here, you could say that VL has drooped because this would be 3 volts, let's say, or 2.5 volts for VL. No good. So any operation here is no good. So that means if I can get this line to operate somewhere here, you're going to be robust to these variations in IL and VS. So what's the worst case? The worst case is when you're right there. Can you see that? And why is this the worst case? Because if you go any more, you're now in a situation where this voltage has actually drooped. Okay, so this worst case scenario says that my current is 0, but my voltage is still good, it's still 5 volts. Now, what affects this thing going up and down? Well, one big thing is this y-intercept, right? This y-intercept, which is this guy, and mathematically you can see is minus Vs over Rs plus IL. Well, what makes this go up? Look at this. B goes up if IL increases. And we talked about that over here. If I'm trying to pull more current, it's going to be harder. And you can see why it's going to be harder mathematically, right? So this is nice because it's matching the math with the physical intuition. What about your voltage? Well, because I have a minus sign here, decreasing Vs is actually going to bring this up. That's also a bad thing. And we saw that here, right? Well, what about this RS? Well, because RS is in the downstairs, increasing RS, not the load resistor, but this RS is also going to be bad. So actually big values of RS, small values of VS, and big values of IL are going to make it harder for this voltage regulator to do its job and keep 5 volts on here. Okay, so with this in mind, we have the worst case scenario with ID as 0 volts, VL is 5 volts. We have VS as 8 volts and IL as 150 milliamps. This is kind of our worst case situation. Let's calculate what RS is going to be to operate here, right? And so what's nice is we have one equation, one unknown from that nodal Ohm's law KCL equation. Okay, ID is 0. VD is now negative 5. Good. Vs is 8 volts, and this is 150 milliamps. And now it's just one equation, one unknown. So I have 5 over here. Minus and minus make positive. I have the negative 8. I have the plus 0.15 amps. And then I just solve for RS. So I get negative 3, negative 0.15. The negatives cancel, and I get 3 over 0.15, which is 20 ohms. So that means that 20 ohms, this is the value of this resistor over here, so that this is robust, even though this current might vary between 50 and 150 milliamps, and this might go between 8 and 12 volts. This will still maintain a constant 5 volts. That's nice. Now, the last thing it asks is, well, what's the max power? Well, let's say this now goes up to 12 volts. This stays at 5 volts. We're going to, by KVL, we're going to have a 7 volt drop across here. That's easy. Just use your power equation. V squared over R, 7 squared over 20. 2.45 watts is the worst case power that this is going to see if you maintain that operating range. Okay, so one last thing I want to do is actually I simulated it. So if we go to our simulation, I'm going to go share screen over here. I put everything in. So I have the 20 ohm resistor. Okay, I have an 8 volt source. I have a Zener diode here with 5 volts. Okay, and what's cool is you can actually choose the 5 volts edit model. You can choose the 5 volt here, right? Breakdown voltage. And I have an ammeter that's monitoring the current. I also have an oscope here monitoring the resistor here. And then I have a voltmeter here. Okay, so if I run this, notice I've tuned this load resistor so that it is approximately 150 milliamps, right? Notice in this orientation or in this situation, look at this, nearly no current goes to the Zener diode. So remember, we were operating at that point, and we are still maintaining about 5 volts across the load. Okay, now if I change this resistance of the load so that it is actually more, so let's say we go to 50 ohms, that is actually going to make it 100 milliamps, and we're like still fine. Look, still about 5 volts, right? Okay. Now let's say we go to, if I go to 33 I go back to 33, which is about 150. I go up here to 12 volts. Let's see what happens. Again, this voltage is still constant, right? So this is all good. Yeah, this starts shunting more current, but that's okay. The voltage regulation is still working. But now let's say I go to 8 volts here, right? Or actually, let's go even worse. Let's go to 5 volts. Look what happens. The voltage drooped, okay? So that you can see how this is not designed to operate below that regime. Good. So let's go back to 8 volts. We're just at the limit. What if I make a smaller resistance here, which is going to pull more current? Let's go to 10 ohms. Okay. What happens? Look, we're pulling now 266 milliamps. Again, the voltage droops. So this is fine. It's when it's within the region that we've designed it, it maintains 5 volts. Okay. Now here's your 20 ohms. At this point here, can we see what power that we're dissipating in the worst case scenario? So what's the worst case scenario? Well, this stays at 5 volts. That's fine. This goes up to 12 volts. Okay. So 5 volts, 12 volts. And if I go here and if you look down here, I'm going to hover over that 20. You can see the power dissipated is 2.38 watts, which is pretty darn close to what we calculated of 2.45 watts. I'm going to put a link to this in the description of this video so you can also play with these values. But I hope you can see that this is the simple homework problem simulated, and you can play with these numbers and see that they match our analysis. Pretty cool stuff. All right, have a great day, and I hope this was helpful. All right, goodbye.